To my channel Science with Anish. So today my first video is going to be about topic of the modern periodic table. So as you can see, this is a periodic table consisting of 118 elements. So firstly, you need to be clarified about these concepts, otherwise you will not be able to understand this video. Hopefully you're clear on these concepts. Now moving on, you can see on the periodic table, I'm gonna dive straight into this. There are two things you can immediately notice: groups and periods. So these are the groups. You can see 1, 2, 3, 4, and they're sitting all the way up till 18. And alongside that, there are several periods: 1, 2, 3, 4, 5, 6, 7. However, you just have to understand groups, and after that you will understand periods by yourself. You can see that some groups are divided into several columns: 1A, 2A, yes, 3B, 4B, 5B, 6B, 7B, 8. So we're gonna dive into that later. So obviously the first column you can see is 1A. So I'm just gonna call it group 1. So in group 1, there are elements hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Now, why is, for example, molybdenum not in group 1? Why is molybdenum in group 6? Why is molybdenum in group 6? Is it because the scientists just chose pick a random number and they picked a random element to put into a random group? No. It's because every element in a particular group is chemically similar, and that is the first point that you will have to note down, and I'm gonna have to make sure you remember this. So write it down somewhere in your head, it's fine. Just remember this: every element in a group is chemically similar. And now my job is to prove that to you guys. So you can see the hydrogen has the atomic number 1. Now if we move to this is an electron dot diagram. You can see I've already drawn many things here, and I have already written duplet LIH. Well, what is a duplet? Well, in order to become stable, an atom needs to attain several shells, and I will explain the concept of shells later. What you need to know is that the outermost shell of an atom is called the valence shell. Hydrogen has only one shell, however it only has one electron. Now an atom needs 2 shells to become stable in its first shell. In its second shell it has 8 shells to become stable. 8 atoms to become stable. Hydrogen only has 1 atom because its atomic number is 1, and as you may have already written, atomic number is equal to number of electrons. So hydrogen has only 1 atom in its only shell, but it needs 2 atoms to become stable, because a duplet has 2 atoms, and an atom can only become stable. An atom can only become stable if it has a complete duplet. If it has a complete duplet or a complete octet. However, hydrogen has only 1 electron, so it can't have an octet. It only can have a duplet. Now if you look at it, lithium has the atomic number 3. So it has a complete duplet, right? Lithium has a complete duplet plus 1 extra electron in its outermost shell. So it will donate its 1 electron to hydrogen, and now hydrogen has 2 atoms in its duplet shell. So now hydrogen becomes stable. Lithium gives its 1 atom to hydrogen, so it forms the compound lithium hydride, where hydrogen now has 2 atoms, 2 electrons. I keep saying atoms and electrons, so remember these are not atoms, these are electrons of the atom. So let me re-explain. Lithium has 3 electrons, right? So it gives it has a complete duplet, because the duplet needs only 2 electrons to become stable. So it has 1 extra electron. So it will give that 1 extra electron, it will donate that 1 extra electron to hydrogen. As you can see, I've written L means lithium. So after lithium has donated its 1 extra electron to hydrogen, hydrogen now has 2 electrons in its shell. So hydrogen becomes chemically stable. Hydrogen becomes chemically stable. And lithium, which got rid of its only extra electron, now has 2 electrons, and it's completely stable. So now lithium is stable and hydrogen is stable as well. Succeeding lithium in the table is sodium. Now sodium has the atomic number 11, so it has duplet of 2 shells, and an octet takes 8 shells to become stable. So sodium has 2 plus 8, 10. So sodium has 10 stable electrons and 1 extra unstable electron. So it will donate that 1 extra electron to become unstable. Potassium has the atomic number 19. So I will explain the concept of shells later, but potassium has 3 shells. The first shell is a duplet having 2 atoms. The second shell is an octet having 8 atoms. The third shell is an octet having 8 atoms. 8 plus 8, 16 plus 2, 18. So potassium has 18 stable electrons and 1 extra electron. So potassium donates 1 extra electron to become stable. So why are hydrogen, lithium, sodium and potassium in the same group? Because atoms in the same group are chemically similar. How are they chemically similar? Hydrogen, lithium, sodium, potassium are chemically similar because they all need to donate or receive 1 electron to become stable. In short, they all need to donate or receive the same number of electrons to become stable. Another example, in group 2, beryllium has atomic number 4, so it has 2 stable electrons and 2 extra electrons because the second shell has 8. So beryllium will donate 2 electrons to become stable. Magnesium has 10 stable electrons and 2 extra electrons, so it will donate 2 electrons to become stable. Calcium has 18 stable electrons and 2 extra electrons, so it will donate 2 electrons to become stable. And like that it continues onwards. So what you have understood is that in a group, all the elements that are in a group are chemically similar because they need to donate or receive the same number of the same number of electrons to become stable. Hydrogen, lithium, sodium, potassium all need to donate or receive 1 electron to become stable, and that is why they are in the same group. If sodium needed to donate 2 electrons to become stable, it would be in group 2. That means that every group has a different chemical similarity. Now we will study about shells first to understand further about this topic. So as you can see, these are just shells in atoms, and these are some numbers that I have written up. So these are not made up numbers, they are not random numbers. These numbers mean something. So firstly, the first shell of an atom is the K shell. As you know, hydrogen and helium, they only have K shells. However, atoms which have atomic numbers more than 2 have 2 shells. So a K shell is stable if it has 2 electrons. Like lithium and beryllium, they donate their extra electrons to attain a stable K shell, which is called the duplet. However, the second shell of an atom is the L shell. Now in an atom which has a L shell, the L shell is the outermost shell of an atom, which means that every atom which has an L shell also has a K shell. So every atom having a L shell also has a K shell, which means that, as you can see, L shell has 8 atoms, which means that it must contain a K shell with 2 atoms, which means in order for an atom with an L shell to become stable, it needs to attain 10 electrons in its outermost shells. 10 electrons. As you know, neon has 10 electrons and it's stable because it has 2 electrons in its K shell and 8 in its L shell. Similarly, argon is stable because it has 18 electrons and the M shell needs 8 electrons to become stable. An atom containing M shell must also have a stable L shell and K shell. So every atom after the atomic number 10 on the periodic table has a stable K shell and L shell because they have more than 10 electrons, meaning their first 2 shells are stable. The M shell needs 18 electrons to become stable. Like potassium and calcium have valencies of 1 and like potassium and calcium need to donate 1 and 2 electrons respectively to make their number of atoms 18 to make their M shell stable. Similarly, the fourth shell is the N shell, which contains 18 atoms. Now every atom with an N shell must contain 3 stable K shells, L shells and M shells, which means every atom with the L shell has a stable K shell, stable L shell and stable M shell. For example, iron has an atomic number of 26, which means it has a stable K shell, stable L shell and stable M shell and 8 electrons in its N shell. The fifth shell is the O shell. Forgot to mention, krypton is a noble gas which has 36 electrons. It has a complete K shell, a complete L shell, a complete M shell and complete N shell. So it has a atomic number of 36, which means 2 plus 8 plus 8 plus 18. So it's completely stable and has no extra electrons. So here is definition. Atoms with no extra electrons in their outermost shell are called noble gases. Atoms with no extra shells in the outermost shells are called noble gases. Now, xenon is the noble gas with 54 electrons. Its outermost shell is the O shell. So it has 2 plus 8, 10 plus 8, 18 plus 18, 36 plus 18, 54. It has 5 complete shells and no extra electrons. As I explained, lanthanum with the atomic number 57 needs to donate 3 electrons to become chemically stable and attain 5 complete shells. The sixth shell is the P shell, which contains 32 atoms. Radon is the noble gas for this shell, which means radon has 6 complete shells. A complete K shell with 2 atoms, complete L shell with 10 atoms, a complete M shell with 18 atoms, a complete N shell with 36 atoms, complete O shell with 54 atoms, and more 32 atoms, which completes the P shell with 86 atoms. Similarly, actinide is an element with atomic number 89. So actinide needs to donate 3 electrons to become chemically stable and complete 6 stable shells. The last shell is the Q shell with the noble gas 118, which is oganesson. Moscovium is an element containing atomic number 116. So it needs to receive 2 electrons to become chemically stable and complete 7 complete shells. So a complete K shell has 2 electrons, complete L shell has 8 electrons, a complete M shell has 8 electrons, a complete N shell has 18 electrons, a complete O shell has 18 electrons, a complete P shell has 32 electrons, and a complete Q shell has 32 electrons. Yeah. And these are the corresponding noble gases. Helium has a complete K shell with 2 electrons, neon has a complete K and L shell with 10 electrons, argon has 3 complete shells with 18 electrons, krypton has 4 complete shells with 36 electrons, xenon has 5 complete shells with 54 electrons, radon has 6 complete shells with 86 electrons, and oganesson has 7 complete shells with 118 electrons. And this is how these 7 noble gases are complete. Now this is the most important thing in this entire video. Till now, I have continuously provided many examples to prove just one simple point, and that is that all the elements in a particular group are chemically similar, which means that they need to donate or receive the same amount of electrons to become stable. And I have also provided a chart which shows the various number of shells and how many electrons you need in every shell for an atom to become stable with 3 examples. Now what are you looking at is every group from 1 to 18, every period from 1A till 0, and their chemical similarity and how complex or easy they are. So you already understand all the elements in 1A, group 1, that are hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. They all need to donate or receive 1 electron to become stable. So they are chemically similar, and that is easy to understand. In group 2, all the elements need to donate or receive 2 electrons to become chemically stable. For example, in group 2, beryllium has the atomic number 4. So it needs to donate 2 electrons to become chemically stable as a duplet. Succeeding beryllium is magnesium, which has the atomic number 12, which needs to donate 2 electrons to become a stable octet, that is attain 10 electrons. Succeeding magnesium is calcium, which has the atomic number 20. Calcium needs to donate 2 electrons to become 18 and become chemically stable as an octet. Similarly, all the elements in group 2 have to attain chemical similarity by donating or receiving 2 electrons, which is also easy to understand. In group 3, if you look at it, there's some interesting facts you should know first. Now if you look at it, we're looking at group 3. This boy right here. Look at it. Scandium, yttrium, lanthanum, actinium. As I explained to you, scandium has 3 complete shells because the closest shell to its complete shell to it is 18. So it needs to donate 3 to become stable. Yttrium has 4 shells because the closest shell to it is the N shell, which has 36 electrons. So yttrium needs to donate 3 to become chemically stable. Lanthanum has the atomic number 57, so it needs to again donate 3 electrons to become chemically stable, that is attain 54 electrons, that is complete 5 shells. Actinium has 6 complete shells, so it needs to donate 3 electrons to become chemically stable with 86 electrons. So we have successfully proved that all elements in group 3 need to donate or receive 3 electrons to become chemically stable. But the real complexity starts here. From group 4 to 9, you will notice a big absurdity. You may notice this. Titanium and zirconium, they have the atomic numbers 22 and 40. And they need to donate 4 electrons to attain 18 and 36 respectively and become chemically stable. However, hafnium and rutherfordium, if they donate 4, then their atomic number becomes 68 and 100, which is not chemically stable. Remember the chart? You can rewind it. 68 and 100, it's not chemically stable. The closest number to hafnium and rutherfordium is 86 and 118 to become chemically stable. So hafnium and rutherfordium need to receive 14 electrons to become chemically stable. Remember, 72 plus 14 is 86, which is chemically stable, and 104 plus 14 is 118, which is chemically stable. But titanium and zirconium need to donate 4 electrons to become chemically stable, but hafnium and rutherfordium need to receive 14 to become chemically stable. Huh? So you've just been lying? Huh? No. These 4 elements, they are not chemically similar. So how can they be in the same group? It's very simple. Now all you have to do is visualize. I will give you a very easy example in which you will understand very easily. For example, there is a cricketer. He has played 100 games in his entire career. Every time he needs 1 run to win of 1 ball, he takes a single. So every single time he plays and he needs 1 run to win, he takes a single. But is it also possible for him to hit a 6 and win the match? Yes. But does he ever hit a 6 and win the match? No. Throughout his career till his retirement, he has never hit a 6 to win the match. He has always taken a single to win the match. But it is also possible for him to hit a 6 and win the match. Similarly, during chemical reactions, titanium and zirconium always donate 4 electrons to become chemically stable throughout their reaction time period. But is it also possible for them to receive 14 electrons and become chemically stable? Yes. Yes. If you see closely, if titanium receives 14 electrons, then it will become 36 electrons, which is electronically stable. If zirconium receives 14 electrons, then it will become 54 electrons, which is also chemically stable. So, similar to how the cricket batsman never hits a 6 to win the match, but it is possible for him to hit a 6 and win the match, titanium and zirconium never receive 14 electrons to become chemically stable because it is easier for them to donate 4 electrons and very hard for them to receive 14 electrons, but it is possible for them to receive 14 electrons and become chemically stable. Similarly, it is easier for the batsman to hit a single and win the match. So why would the batsman hit a 6 and win the match if he can just get a single and win the match? Similarly, why will titanium and zirconium receive 14 electrons to become chemically stable when they can donate 4 electrons to become chemically stable? However, is it possible for them to receive 14 electrons and become chemically stable? Yes. So even though throughout the chemical reaction, titanium and zirconium never in their entire history of the universe have received 14 electrons to become chemically stable, it is still possible for them to receive 14 electrons and become chemically stable. Similarly, throughout the career, the batsman has never hit a 6 to win the match, but it is possible for him to hit a 6 and win the match. Rewind and understand. Similarly, hafnium and rutherfordium in the same group as titanium and zirconium can also receive 14 electrons to become chemically stable. Look at the chart. Group 4 plus minus 14 complex. All elements in this group need to donate or receive 14 electrons to become chemically stable. One more time. If the batsman has never hit a 6 in his entire match, is it impossible that he will hit a 6 to win the game? No. But he has decided never in his career to hit a 6 and win the match because it is easier for him to get a single. Similarly, the chemical or the element titanium and zirconium never receive 14 electrons because it is much harder for them to receive 14 electrons. But it is chemically possible. And because it is only chemically possible for titanium and zirconium to receive 14 electrons to become chemically stable, and it is also chemically possible for hafnium and rutherfordium to receive 14 electrons to become chemically stable, these 4 elements are chemically similar and these 4 elements are in the same chemical group. Rewind and understand. For the final time, I will make you understand. For example, Sachin Tendulkar. He has played 100 games in his entire career, and 100 times he needed 1 run of 1 ball to win the match. Every time he took a single to win the match because it was easier for him to hit a single to win the match than hit a 6. But was it impossible for him to hit a 6 and win the match? No. He could have hit a 6 and win the match as well, but he chose not to. Similarly, the atom chooses not to receive 14 electrons and instead donates 4 electrons because it is easier for the atom to donate 4 electrons and harder for the atom to receive 14 electrons. Similarly, it is easier for the batsman to hit a single and win the match and harder for the batsman to hit a 6 and win the match. That is why the batsman always chose to hit a single and win the match, and that is why the element always chooses to donate 4 electrons and never chooses to receive 4 electrons, but it is chemically possible. That is why these 4 elements are chemically similar, because all the elements in the group 4, well, they all are possible to become chemically stable by receiving 14 electrons. Hopefully you understand. In group 5, if you can see, in group 5, vanadium and niobium, well, they can donate 5 electrons and become stable using 18 and 36 respectively. However, tantalum and dubnium need 13 electrons to become 86 and 118. So tantalum and dubnium need 13 electrons to become chemically stable. Well, if you look at it, vanadium and niobium, even though they always, every time donate 5 electrons to become chemically stable, because it is easier for them to donate 5 electrons and harder for them to receive 13 electrons, it is still chemically possible for them to receive 13 electrons and become chemically stable. So all these 4 elements, it is chemically possible for them to receive 13 electrons and become chemically stable. Same goes for group 6, same for group 7, same for group 8, and same for group 9, and same for group 10. If you understand the process that I've been explaining you, then you will easily be able to understand why this law is true for all these groups. From then on, it's comparatively easy. Now the next group we will look at is group 15, 16, 17. In group 15, 16, 17, all the elements also need to donate or receive 3, 2 and 1 electrons to become chemically stable. So why are the elements in group 15, 16 and 17 not put in the same group as group 3, 2 and 1? Why are they? Well, it is because the elements in group 15, 16 and 17 have different chemical properties than the elements in groups 3, 4, 5. So even though they are chemically similar, I'm rewinding. If you look at it, the elements in group 1, 2 and 3 need to receive or donate 1, 2 and 3 electrons to become chemically stable, and the elements in group 15, 16 and 17 need to receive or donate 3, 2 and 1 electrons to become chemically similar. So why are the elements in group 15, 16 and 17 not in the same group as elements in group 1, 2 and 3? Well, that is because the chemical properties of these elements are different. Simply put, the chemical properties of these elements are different. And why does group 18 have 0 as its period? And why are they stable? That is because in group 18 there are 7 elements, which are helium, which has an atomic number 2, which is an electronically stable number; neon, which has number 10, which is chemically stable; argon, which has the number 18, which is electronically stable. Krypton with the number 36, that is chemically stable. Xenon with the number 54, which is chemically stable. Radon with the number 86, which is chemically stable. And oganesson with the number 118, which is chemically stable. So all the elements in group 18 are chemically stable. Hopefully you understand everything about arrangement of elements in periodic table. Now to recap these concepts, all you need to do is pause the video and look at it. Thanks for watching. I will come back with the next video, a review of the human skeletal system.